Stars Quantum.
Hey, hi. I'm very honored to be here for the second round in my tour. The first tour started last week. Hello, hello. Yeah, that's fine. That's fine. Okay. I mean, so the first tour. Okay. I mean, the tour started last week. Okay. At Hwa Chong Institution. Okay. So this is the second tour stop. And basically, the talk today, we are talking about Monte Carlo methods in engineering. All right? And basically, I am Tama. Yeah. Okay. Hello. 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 Okay. So I am Tama from High Technologies. And basically, we are stationed at the NUS Enterprise. And basically, we, yep. So we want to talk about this method. Can we go on? So before we start, before we start venturing into the topic itself, all right. So we want to talk about that. We want to talk about this public lecture that we have right now. And basically, they will be the last 2 weeks of June, okay? And basically, there are web technologies and numerical mathematics, okay? And we would like to invite our students to come, and they will be free of charge for students from the places that we give our outreach talks to, all right? So we will spread around the forms, and so you can just fill them up if you are interested in. And the place that we will host our public lecture will be at Center for Quantum Technologies. Right. Next slide. Okay, so we start talking about Monte Carlo method. All right. All right. So we are talking about applied mathematics. All right. Applied mathematics, okay, is of course very important. All right. If you do not have applied mathematics, basically there's just no science and engineering. All right. The entire industry is actually geared by applied mathematics as well as computational science. Okay, and there are two branches. The first branch is deterministic, okay, and the second branch is stochastic, right? So what is like deterministic? Deterministic is something like solving differential equations, all right, like dy dx plus y is equals to whatever number, right? Then there are some certain ways that you can just do it systematically, all right, like. There are some sort of a fixed formula which you can use, and basically students up to the pre-university training are very good at doing this, okay? But very often, students just completely ignore this part, okay? A stochastic part, which makes them very weak when they when they come to university, all right? Because mainly, deterministic methods can only work for very limited problems. Like for example, you want to solve something like 1 million times 1 million matrices, then you can still use the deterministic. But if you want to solve a size that's larger than that, then simply there's just no chance for you to do that. And so today we will talk about the stochastic branch. All right. So we start off, okay, by highlighting the simplest example, which is just to evaluate pi. All right. Now you imagine that there is a square of 1 times 1. Okay. We just look at the simplest example, and within the square there exists a quadrant. Okay, and we know that the area of the quadrant is just pi over 4, and the square is just 1. Okay. I hope that you know this. Okay, or else you can't be here, all right? And so the ratio of the two is just pi over 4. And if statistics work, then you just keep on throwing stones into this area here. Then what you will find is that the number of times that you hit this quadrant to the number of times that you throw has to converge to pi over 4. All right? I mean, if this doesn't work, that means you are telling me that mathematics doesn't work. Okay? I mean, this is actually due to the central limit theorem or the weak law of large numbers, which we can simply prove in 4 lines. Okay? I mean, why central limit theorem works is actually in these 4 lines of proof, but I will not. I will not go through it. You can just copy it. Now, what happened? I mean, what it simply means is that the probability that your Monte Carlo measurements to your real quantity, when it is greater than some threshold, okay, it must be smaller or equals to some sigma square divided by m or epsilon square. Now, what this means is just that with a larger and larger sample trials, okay, I mean with larger and larger sample trials, then what happened is that you will find that the Monte Carlo answer will be more and more accurate, okay? I mean, and the error scales with 1 over square root m. All right. Now, why we want to do that is because it is the only method that works. Okay, it is the only method that works for large simulations, and basically you know that in the next decade or the next 2 decades, the whole industry will be largely driven by big data. Okay, so this method will be more and more required of you. I mean, this is not. I mean, you can study it or not. I mean, this is a must topic that you must study. All right, and this is numerical exact. Can you go to the next slide? Now we can simply write a code. All right, so this is a USCOPI code. Basically, once you write this, and what you will see is that the value of pi over 4, okay, I mean the exact value is something like 0.785. Okay, this is pi over 4, and what you will find is that after after 100,000 trials, you will find that the pi over 4 is 0.783 to some error. Then what you will find is that if you keep on throwing and you will keep on measuring every 100,000 trials, you will find that around 2 million trials, okay, the numbers is almost exact. Okay, I mean, what do you mean by almost exact? Almost exact means that up to some decimal places, okay, you can accept the, you can accept the number. And normally how you will do it is that you look at, can you take away the mouse? Yeah, correct. Now, if you look at the error like 0.0002, then normally you will just need to multiply a factor of 5. This will give you roughly like 0.001. That means you can trust your number to the 3rd decimal place. Okay, normally this is how you do. Okay, and okay, what do you mean by the error? The error means that, okay, that your this is the number, okay, this is the sample trial distribution, and because of the central limit theorem, okay, this is largely normal. And what I mean is that 63% of the time, okay, you can trust that your number, that your true value actually lies within 1 sigma, all right? And when you have your, when you multiply this number by 5, okay, that means this is a 5 sigma range. And so therefore you can have more than 99% of the chance that you can actually trust it. And this is very often known as a 5 sigma test, all right? Now, and this is a very good, okay, this method is known as direct sampling, all right? This is very good for actually calculating of bounded multi-integrals, all right? I'm not interested in calculating integral, but I'm more interested in calculating 100 integrals, okay? And basically, there's just no way that you can solve it by your pen and pencil, right? Okay? All right, yeah, can you go to the next slide? Okay, now we have a second example, okay, we talk about Gaussian integrals, okay? Now, all distributions in nature, all right, becomes increasingly normal with bigger samples, all right? This is the 2nd time or the 3rd time that I'm speaking about this, because this is the most important to me, this central limit theorem is why nature works. This central limit theorem is why we are living in this world. Okay, I mean, if there were no central limit theorem, there's no quantum theory. All right, but basically, it is this central limit theorem that that we are basically talking now. All right, so this is what I feel. This is the foundation of science. Okay, but if you ask, if you ask some other people, then basically he will tell you some other things. All right, but if you ask me, then basically I will tell you the central limit theorem is the foundation of science. All right, and because it is normal, okay, that means you can do some forecast. All right. Well, I mean, when you want to do some forecast, okay, then my question is, okay, how long can you do the forecast, right? I mean, I would say that for very short time, and basically this is probably yes. Okay, you can do some sort of forecast. Now, before I continue, I will want to raise the first brain teaser question. Basically, this is an interview question at a G Research hedge fund in London. And basically, this is related to the topic of financial engineering. Now, the question is, a stock has beta of 2.0, and the stock volatility is 0.02. Now, I mean, suppose that yesterday's closing price was 100, and today the market goes up by 1%. Okay, now the question is, what is the probability of today's closing price being at least 103? Okay, so if anyone can answer this question before I change this slide, I'm going to buy you a small drink. All right? All right, but okay. I mean, before that, let me just let you get your lunch or get your free drink closer. That is basically volatility in a hedge fund or in financial market. It is known. I mean, it's the same thing as a standard deviation. Okay. I mean, we call it a standard deviation, but the financial guys just call it volatility. But so I mean, they are just sigma. All right, and basically, we have some beta. All right, the beta is just a reflection of how your stock behave relative to the market. All right. Okay. Suppose you talk about the markets in Hong Kong. Okay, then that means we are looking at the market of the Hang Seng Index. Or if you are talking about the market in New York, then we are looking at the Nasdaq. Okay, so we want to say, I mean, the beta of 2.0 means that your stock will behave, okay, I mean, will behave twice, okay, like the market. Okay, all right. So let me continue. So now, can you just give the answer to the front desk trader? All right. And the front desk trader needs your answer fast, you know, because the numbers keep on changing on the board, right? So you have to tell me the answer right now. All right. Okay. And okay, I mean, while you work on this, I will just continue. Now, Gaussian integrals, I mean, what is Gaussian integrals? Okay, I mean, why are Gaussian integrals so important? Because all distributions in nature, okay, all distribution in nature tends to be normal, okay, with larger and larger sample trials. That means we always, we always would want to measure some quantities called the moments, all right? Why the moments? Okay, the moments means, I would want to get some characteristic behavior, all right? So if you, the second, if you look at the second moment, then that's somehow related to the variance or the standard deviation. If you look about the third moment, then we are talking about skewness. That means you want to look whether the stock is going up or not. Now, if you look at the fourth moment, then that is the kurtosis. The kurtosis is basically a measure of a heavy tail or the extreme value. Extreme value events. Okay, like, okay, I mean, if it is normal, then the kurtosis is exactly free. So basically, the second chance that you might get your free drink is that, can you give me a proof of this? Okay, and basically, if let's say I have my I have my stock data, and I calculate the kurtosis is significantly more than 3, okay, that means I am very sure that I should leave the market, okay, because I am not doing a forecasting, I am doing a gambling, okay, okay, because only if your sample data, okay, is forecastable, then I could then I can basically make some money, right? Okay. If it is more than 3, then I know that I could not do forecast. Then I'm just a gambler, and I do not want to gamble my career away, right? Okay. But then you will make a lot of money, right? or then you become bankrupt. Okay. Now, and basically we want to do the Markov chain Monte Carlo. Okay. Basically, we will want to speed up the random. We want to speed up the random process. We want to speed up the random walk, okay? Now, if you look at the case that we have last time, that means you keep on throwing the stones, all right? If you keep on throwing the stones, okay, that means each new trial of stone is not dependent on the previous trial, right? So they are independent measurements, okay? But now I would want to think of something that suppose I do not mind too much about the independent trials, okay? If we can accept some sort of a dependency between the trials, okay, can we speed up the random walk to a large factor or not? Okay, and basically, when I write it here, that means it basically that should work lah. Or not, I will just not write it here, right? Now, the strategy. Okay, because I only have 1 hour, so I could only give you some very brief highlight. Basically, you should hear of the name called important sampling. Okay, that means like 1-2 years later or 3 years later when you go to the university, then you will definitely hear the name called important sampling. And basically, Markov chain Monte Carlo, it satisfies the principle of ergodicity and detailed balance. Detailed balance is also equilibrium condition. And the practice normally is Metropolis algorithm. Okay, so before I go on, is there any answer from the crowd? So what is the probability? No? No, lah. No, that is a pure guess. Okay. You cannot lah. You see my. He saw my answer already. Okay. What's the number that you want to give? Any more trials? Any more trials? 75% no. 47.3 no. What? 5.1% no. Okay, no. Okay, so I would safely say that you have to wait for my next trial to get my drink. Okay, so can you go to the next slide? Now, now I give you the answer here. Basically, when we talk about the beta, it's just nothing but the return of the stock divided by the return of the market. I would say that since the market goes up by 1%, okay, I would safely say that the stock would go up by 2%, okay, because the beta is 2, right? Okay, now that means the return of my stock will scale as 0.02. Now this is my this is my expected return, and I tell you that my stock volatility is 0.02, right? Okay, so that means my return will actually scale as this random, as this normal distribution. And so now my question is, what is the probability that the return is greater than 3%, right? Because my question is, what is the chance, okay, that the price can go up beyond 103, right? So that's a 3% gain. And so this is just the same as the probability of the standard normal being greater than 0.5, and so this is roughly 0.31, and this is actually taken from the normal table, okay? And in this, class, I will teach you how to I will teach you how to get your numbers without going to the normal tables. Okay, I mean, you can actually do it by your computer. Okay, so what I'm saying is, okay, I mean, I'm integrating the normal distribution from 0.5 to infinity, and this will give me 0.31, all right? And basically, this is what I want to do. Now, if you follow classes, okay, then you will know that this thing here is known as a probability density function, okay? Basically, this is your probability distribution, and it is normal. That means it will take this shape, all right? It will take this shape, and basically, I would ask for the area that is shaded by the orange arrows. And you can do likewise by Markov chain Monte Carlo, which I would very fast go through it. Basically, you rewrite your whole thing. Okay, that means you will rewrite this quantity. You will rewrite this quantity in this particular form. And then you will call this as the weight. Okay, as the configuration weight. And you do random walk over the configuration weight. Okay, or I should speak it more vigorously. That means you are doing a random walk in the space of Z, but it is weighted by the fz function. Okay, so you will roughly, you'll be convinced that, the more, the more probable, okay, the more probable that your fz is, the higher the chance that the random walk will be there. Okay, so you will say that, you will roughly say that this will be optimal to the fz distribution. So basically, you will need to do something like the detailed balance, and basically we need to do important sampling, and these are known as smart random move, and they are not independent. Okay, that means you cannot trust the error, but to some extent you can still trust it. Okay. Now I want to give you another question. Okay. Now the other question is like that. Likewise, I will also buy you a drink. Okay, if you can prove to me that the integral from negative infinity to infinity of e of minus x squared dx, okay, if you can prove to me that this is square root pi, then we see each other in the canteen, all right? Okay? Okay? Now, this type of integrals are known as Gaussian integrals, and they are the most important integrals in statistics, in financial engineering, as well as in quantum statistics. All right? So these are very important. So again, so if you can do a proof, then we will see each other in the canteen. Okay, so can we continue? Okay. So, so we will continue. Now, what do I mean by Markov chain Monte Carlo means that the random walk is like Z1 to Z2 to Z3 and so on, okay? So each point on your random walk, okay, is actually dependent on your past, okay? So there's some sort of history going on. And what do I mean is that the probability of say, that you want to move from Z2 to Z3, okay, must be balanced by the probability that you move from Z3 to Z2 by this particular ratio, okay? And so this is some sort of, say, the so-called detailed balance, all right? Detailed balance means, there are many terms of re-saying this term called the detailed balance. Some people say, okay, some people say that there is a steady state. Some people say that there is, I mean, there is a statistical equilibrium. Okay, no matter how you say it. Okay, I mean, these are known as a detailed balance. And the Metropolis algorithm in 1953. Now, this is the highlight. Now, basically, this automatically satisfied detailed balance. Can you see why this is true or not? Can you see why this is true? I mean, can you see that? Now, I mean, can you see that if your probability is defined in this way, then this is automatically satisfied? I will talk about this at the end. Okay, and so another thing is known as another condition is known as ergodicity, means all configuration must be accessible. So you want to reformulate this guy. Okay, so you want to ask this question. So you can write a simple Markov chain code, which is not more than 20 lines, and you will get the same answer. That the area that you sum over the right and you sum over the left is something like 0.61763. But when you divide by 2, this will give you your 0.308, right? Yeah, I mean something like that. Yeah, thank you. So this actually works. Okay, so I've given you an example that works. So before I continue, is there anyone that can prove this? No? No? I mean, you are not doing too bad compared to Raffles, because Raffles also could not prove it. So, really? No attempt? No attempt, huh? Yeah, no lah. Okay, so I will talk about the proof right now. So the proof is actually very simple. Okay, I mean, after you hear about it, you will find that why I do not know about the proof. Now you know that if I define I as my integral, okay, so this is nothing but a number, right? So this is not nothing but a number because it always integrates to just some number. Then we know that as a number must be I times I, and you just take the square root, right? Okay, all right. So this is nothing but you do a double integral Am I correct? So I mean, this is just I, right? This is just I, right? Right? Yeah. Now this is just the square root of a double integral. Can you see from the back? This one you cannot see, right? From the back. Can you see this? All right. So this is nothing but, now I define. Now this is my x1 axis, this is my x2 axis. Okay. Now I define the polar coordinates. At some point, this is r. And I can define some angle called theta, or I define as phi.